We're going to do a few more examples here with finding volume from cross sections. So in this problem, we're using the same base as above. So I've redrawn it, that square root of x bounded by 0 and 4. Now cross sections perpendicular to the x-axis are semicircles. So what this means now is if I make slices across the x-axis, then what's popping out of the page at me is a semicircle. And so let's draw this. So if I make these little lines, the red portion, that's going to be the bottom of my semicircle. And then I've got the semicircle popping out. So we need to find the area of this region. So the diameter is that distance on my region, so that is just square root of x. You could do top function minus bottom function here, especially if there's two curves you're working with. In this case, our top function is root x, our bottom function is 0, so we're doing root x minus 0. So that's my diameter, which means that my radius will be root x over 2. This is a semicircle, so the area of a semicircle is 1/2 pi r squared. So I'm going to have 1/2 pi times root x over 2 squared. So let's simplify that. I get 1/2 pi x over 4. So that is pi x over 8 is my area of a single semicircle. And we remember to find the volume, we integrate the area function. So pi x over 8 dx, my x values go from 0 to 4. Okay, and so if you actually anti-differentiate, you get pi as the volume of this region or this solid. A couple things to notice here is that if cross sections are perpendicular to the x-axis, then our integral is going to have to be in terms of x, because when we're slicing, our slices are going to be perpendicular to the x-axis. So we're going to end up with vertical line segments in our region, which tells us that we have to integrate with respect to x. In the next problem, we're going to see that we have things perpendicular to the y-axis, so we're going to integrate with respect to y there. So really, the problem is going to tell us whether we're integrating with respect to x or with respect to y based on which direction our cross sections are perpendicular to. We also notice that like the bounds on the integral are dependent on the region, like this region, not on like the semicircle versus the square. Okay, so just a few things to notice. So let's see, this one, the base is the region bounded by the y-axis by y equals 4 and by y equals e to the x. So the region that we're looking at here is this one here. Okay, and now it says cross sections perpendicular to the y-axis. So now we're slicing this way. And what's popping out of our page now are rectangles where the height is 3 times the width. Okay, so what I'm going to do here is I'm going to kind of draw on my region. So what I have is a rectangle. That's the bottom of the rectangle. The rest of the rectangle is popping out of the page. Okay. So the length of the bottom of the rectangle is the length of that little red section. That's going to be right minus left because we're working in the y direction. So my rate function is the e to the x function, but I need it in terms of y, so that'll be ln of y. And my my left function is 0, so I'm just going to have ln of y as that length. And so this tells us that the height is 3 times the width, so this tells us that the height of this rectangle is 3 ln of y. The area of a single rectangle will be length times width, so that will be 3 ln of y quantity squared. So the volume of the solid will be the integral of those areas, ln of y squared dy. Now I'm integrating, my bounds come from the region that I'm integrating over, so I need my y values. The y value down here is 1, that's where e to the x crosses the y-axis, so I'm integrating from 1 to 4. You can type this in a calculator. I don't think this one's super nice to anti-differentiate. We get 7.791. Okay, you could also just set up the integral, which is totally okay. Okay, let's do one more together. Okay, so we have the region bounded by y squared, which is a sideways parabola, and 4 minus y squared, which is another sideways parabola in that direction. This is 4 minus y squared, and the black line was y squared. Okay, so the region we're looking at is this region. This region looks like it's going to be best to integrate in terms of y, so I sure hope that they're talking about cross-sections perpendicular to the y-axis, and indeed they are, so that's good. So they say that the thing popping out are quarter circles. So what's popping out of the page is a quarter of a circle, and the radius of the circle is that distance because the radius is in our region. Okay, so we're going to get a quarter of a circle. It's a very sad quarter circle. This is my radius. My radius is the length of this line segment, so we're going to do right minus left. So my right function is 4 minus y squared. My left function is y squared. Okay, and so the area of one of those semi-quarter circles, sorry, is going to be 1/4 pi r squared. So that'll be 1/4 pi times this radius, which let's simplify that just a little bit. So 4 minus 2y squared, quantity squared. So our volume then will be the integral. We need to know these two values. You can set those two functions equal to each other to find those values. We end up getting negative root 2 and positive root 2. So I'll go from negative root 2 to root 2 of my area function, 1/4 pi 4 minus 2y squared, quantity squared, dy. And let's just set up the integral, not actually calculate it here.